All right, it's 9:20, time to start. Good morning. How's everyone doing? So today we're going to start talking about the Chandy-Lamport snapshot algorithm in more detail. We started to talk about it last time, but we didn't really write down the algorithm. We just looked at a very simple example. So today I'm hoping to go back to that simple example, but actually write down what the algorithm does, and then we'll go through a slightly more sophisticated example. Before I get into that, though, I want to come really briefly back to the quiz question last time. So, as you know, we do these quizzes every day in lecture, and most of the time I'm pretty happy with the answers to the quiz questions, but it seems like a lot of people struggled with this one last time. So this was the quiz question last time. Can you use vector clocks to establish a total order of events in a distributed system? And so the answer is no. And the reason why, just to sketch it out for you, to go back to the dot cam. So here's our example of a total order anomaly again. And we talked about this last time, but it might not have been quite spelled out in detail. So if you have a pattern of messages that goes like this, and you tried to put vector clocks on those messages, according to the causal broadcast algorithm that we talked about, then the vector clock on this message here, because so suppose these are P1, P2, P3, and P4, the vector clock sent along with this message would be 1, 0, 0, 0. So that would be the vector clock sent along with both of these messages. And the one sent along with this one would be 0, 0, 0, 1. And just to refresh your memory, that's because the vector clock counts this one send that's happening on the sender as an event. So these messages arrive here, they get delivered. This message arrives here. The current clock on P3 is 0001. The clock on the arriving message is 1000. That's okay to deliver because it's one bigger than the current clock on the process in the sender's position, and it's less than or equal to the current clock on the receiver in every other position. So this is okay to deliver as well. And then and likewise, this one is okay to deliver. So these two events here, if you were to use the vector clocks algorithm that we talked about before, where we actually assign vector clocks, or where we actually count both sends and receives as events, what if you did that? What if you were just kind of looking at this exchange of messages after the fact, and you wanted to assign vector clocks to events? Well, okay, so this one would be 1000 here. This one would be 0001. Suppose you counted the receive as an event here. Then this would be like 1, 1, 0, 0 here. And then this would be 0, 0, 1, 1. And then this coming in here would be what it would, you would take the max, right? So it would be 1, 1, 0, 1. And this one here, you would again take the max, so it would be 1, 0, 1, 1. So these would be the vector clocks of these two events at the end of this whole run, if you were using the vector clocks algorithm that I originally showed. Yeah, okay, so there's a question in chat about broadcasting. So forget about the causal broadcast algorithm for a moment, and just think about assigning vector clocks to events. Oh, okay, a question in chat is, don't we count receives as events? Yeah, that's right. Okay, so that's right. I'm sorry, I got it wrong. So this would be 0021 here. And then this would be 1201 here. So So the algorithm for assigning vector clocks to events that I originally showed works regardless of whether they're broadcast messages or not. So just think about that. So we get here, right? And we have these two events, which have these two vector clocks, 1201 and 1021. Do these two vector clocks have an order according to the order of vector clocks that we talked about? No, they wouldn't. So it's not the case that this one is bigger, right? Because it's smaller in this position. And it's not the case that this one is bigger because it's smaller in this position. So there's no order here. So in other words, these two events here are concurrent because their clocks don't have an order. And so vector clocks alone aren't enough to establish a total order. That's kind of the point, in fact. So some people struggled with this question. And in fact, I got some kind of interesting answers to the question. Some people said things like, well, no, you can't establish a total order of events with vector clocks because events can fail. Like there is some discussion of failure. But failure, I mean, even leaving aside failure, this fact that you can't establish a total order of events with vector clocks is still true because of basically what I illustrated here. Because vector clocks, just like the happens before relation is a partial order, the vector clocks exactly capture the happens before relation. They give you nothing more nor less than the happens before relation. And so the happens before relation gives you a partial order. Vector clocks give you a partial order. They don't give you a total order. Okay, that's kind of all there is to say about that. But I wanted to bring that up because it seemed like there was a little bit of confusion. But today we're going to go back to talking about the Chandy-Lamport algorithm. Okay, so Chandy-Lamport, it's an algorithm for taking a snapshot of the state of a distributed system, and it works by having every process snapshot its own state in a way that can then be put together in a way that makes sense. And an interesting thing about the Chandy-Lamport algorithm is that any process can start it. It doesn't have to be there doesn't have to be like one designated coordinator process or anything like that. So any process can begin it, and that process does not have to announce to everybody, okay, I'm going to start the snapshot now. It can just go ahead and start, because it turns out, as we'll talk about later, it turns out that there's no problem if two processes happen to start taking a snapshot at the same time without coordinating with each other. That turns out actually not to cause a problem for the algorithm. So just for the sake of example, we'll say that there's one particular initiator process for now, but it turns out that nothing would go wrong if there were more than one. So question in chat, does the Chandy-Lamport algorithm help us avoid that total order anomaly? No, it does not. So this is a different topic now. I was only talking about that because I wanted to clear up any confusion from that leftover quiz question yesterday. So this is a different topic. Okay, so this is about taking snapshots in order to look at the state of a distributed system at a given moment and then maybe use that snapshot for things like debugging or answering questions about the system. Okay, so we're going to say one particular process kicks things off, and we'll call it the initiator process. So here's what the initiator process does. First thing it does is it records its own state. Right after doing that, before doing anything else, it has to send a marker message and we're going to draw those using squiggly lines out on all its outgoing channels. So it has to do that right after recording its own state before doing anything else. It's important that that happens, otherwise bugs could be introduced. And it starts recording the messages it receives on all its incoming channels. So in our example from last time, let's say that process 1 is the initiator. So P1 is the initiator. Let's say it takes a snapshot, starts taking a snapshot right after this event A. So here's its snapshot of its state. We'll call that S1. So it records its state. It'll send a marker. We'll say this message C happens over here. This is the same example as last time. It sends a marker. And it sends that marker right after it snapshots its state. Also, it starts recording on all its incoming channels. So in this case, it only has one incoming channel, the channel from process 2. And we said that the convention for naming channels is that, so channel C21 is the channel from process 2 to process 1. So process 1 is now recording on channel C21. That's an equals sign there. So in general, channel Cij is the channel that goes from process I to process J. That's just the naming convention that we're going to use. Somebody in chat asks, what's included in a snapshot? So a snapshot captures all the events that have happened on that process so far, ever. So in other words, it's the current state of that process. Okay, so that's what the initiator process does. Next thing we have to talk about is what happens when somebody receives a marker message, as just happened over here on P2. So we'll bring this initiator page back later if we need to look at it. So receiving a marker. Receiving a marker message. We're going to say when process PI gets a marker message on, let's say, channel CKI. So that's the channel from process PK to process PI. There are two cases in this case. So if it's the first marker message that process PI has seen, here's what happens. PI records its state. PI marks channel CKI, the channel that the marker message came in on, as empty. And PI sends a marker out itself on all its outgoing channels. So its outgoing channels, because it's process I, all of its outgoing channels are going to start with I. So Cij represents all of its outgoing channels. And then finally, it starts recording incoming messages. On all its incoming channels, except CKI, which was the one that the message came in on. So that's a lot of stuff. So the short version of this, record your state and start recording incoming messages. That's what you do when you receive a marker message and it's the first marker message that you've seen. So that's one case. The other case is if it's not the first marker message that you've seen. So what counts as seeing a marker message? Well, we say that if you've done anything at all with a marker message, then you've seen a marker message. So even sending a marker message counts as seeing one. So let's look at the other case. I'll put this back here so that we remember the names of things. So we're looking at the case when process PI gets a marker message on channel CKI and process I has already seen a marker. Here's what we do. PI stops recording on channel CKI. Because it's already seen a marker, we know it had started recording, right, when it saw a marker previously. So we know that it's already recording on this channel. So when it receives a marker message on this channel, and it's not the first marker it's seen, it can stop recording on that channel now. And what does it do? It sets that channel's final state as the sequence of all the incoming messages that arrived on CKI since recording began. So if we look at our picture, so we were in a situation like this, right, where we had captured the state on P1. P1 had sent a marker. Maybe there were some events over here. So in our example, when P2 receives the marker message, it records its state. And this is going to be the case where it's the first marker message that P2 has seen, right? So it records its state. It marks the channel that the marker message came in on as empty. It has no other incoming channels to record on, so it doesn't have to do that. And then it's going to send a marker back to P1. And it's going to mark channel 1, 2 as empty. Now, process 1 over here was recording. Recall that it was recording on the channel, on its incoming channel, right, from the time that it sent this marker message out. Process 2 over here is going to set C1, 2 as empty. So what's going to happen here on P1? So this is actually the already seen a marker case when this marker message right here is received on P1. At that point, P1 stops recording on the channel that the marker message came in on, and it sets that channel's final state as the sequence of all the incoming messages that arrived there since recording began. So in this case, the way that I drew the picture this time, we said that this event D is the arrival of this message from P2. Had this happened differently, had this marker message over here arrived earlier, then maybe this wouldn't have happened, right? Now, one interesting thing to point out is that, remember how we said that in the Chandy-Lamport algorithm, there are these channels, and channels behave like FIFO queues? Well, because of that FIFO behavior, messages can't cross over each other. So you're not going to have FIFO anomalies. So this this FIFO anomaly won't happen. And furthermore, a FIFO anomaly like this, a message crossing over, won't happen between an application message and a marker message either. So it's actually very important that this application message from here, from event C to event D, and this marker message that got sent here, these aren't going to cross over. So if event C happened over here and it got included in the snapshot, and then the marker message got sent after that, well, this marker message won't cross over the application message in the channel from process 2 to process 1. So if this send happened here, it essentially means that this marker message here cannot arrive on P1 until this message arrives first. Okay, so in this particular picture, C21 is going to stop recording now, and it has one message in it. That message doesn't really have a name, but we'll call it like C arrow D to represent the fact that it was a message from event C to event D. So this assumption that messages arrive in FIFO order is very important. Channels act like FIFO queues. Okay. So now what? Are we done taking our snapshot? Well, we've taken a snapshot on both channels, or we've taken a snapshot of the state, excuse me, on both processes. So we've got state snapshots on both processes. And the other thing that processes were supposed to snapshot were the channel states. Well, process 1 only had one incoming channel to record on, and it did. It recorded the message from C to D on its incoming channel. Process 2 only had one incoming channel to record on, channel 1, 2, and that one ended up being empty. So we are actually done. We have everything recorded. We got the state of process 1, we got the state of process 2, and we got the state of both channels. So this snapshot is done. Yay. So hopefully I convinced you last time that this snapshot makes sense, in the sense that there's nothing included in it that would violate causality, right? So B is in there, which means that the thing that happened before B, A, is in there as well. Now, depending on how long this marker message here took, right, to get from process 1 to process 2, different things could have occurred, right? So had this marker message been just a little bit slower, right, it might have arrived like right here before event C happened, in which case process 2's snapshot of its own state would only capture B and not C. And then this marker message would get sent back like this. Now here's where that FIFO thing is really important, right? Because suppose that this marker message got sent here right after the snapshot was taken. This is why it's so important that you send markers immediately after taking a snapshot before doing anything else. But suppose it had crossed over here. Suppose it had crossed over like this. Well then, when process 1 got that, it would take a snapshot like this at the point where it got the marker, right? And then that would be no good, because then these would both be included in the snapshot, but C wouldn't, and then we would have a problem. So this FIFO behavior is actually very important. Okay, so I think I wrote down the most important things that we need to know for the algorithm. So here again is what the initiator process does. So it records its own state. It sends a marker message on all its outgoing channels, and it starts recording on all its incoming channels. And then coming back to the cases of what you do when you receive a marker message, here's the first page of that. So when a process PI gets a marker message on one of its incoming channels, if it's the first marker that it's seen, it records its state. So you record your state just as soon as you see the first marker message. You mark the channel that marker message came in on as empty, and you send a marker out on all your outgoing channels. And then you start recording incoming messages on all your incoming channels, except for that one that the marker message that just came in on, because that one, you've marked that one as empty. And then the case where you've already seen a marker, and you get another marker, you stop recording on the channel that the marker message came in on, and you set that channel's final state as the sequence of all the incoming messages that came in on that channel since recording began. Okay, so there was a question right here about why C12 was empty. Okay, so C12 is the channel from process 1 to process 2. So it's empty because when process 2 receives this marker message, wherever it is that it comes in, let's say that it came in here. So the first thing this process does is record its state, and then the next thing it does is it marks the channel that the marker message came in on as empty, and it only has this one incoming channel. So that part of the algorithm is right here, where we say the process marks the channel the first marker comes in on is empty. Okay, so that's the Chandy-Lamport algorithm for a really simple example. But hopefully even that simple example kind of illustrated why it is that the algorithm cares about FIFO ordering. And I want to walk through a more sophisticated example now. There's a couple of questions here. Yeah, so some folks are asking, like, what's this for again? What problem does this solve? Yeah, okay, so the problem that this solves is it's really hard to know the state of a running distributed system, right? And you could ask everybody, what their state is, right? But when you do, how do you know that, if you ask one process what its state is, and you ask another process what its state is, and you ask another process what its state is, then how do you know that those, when you put those together, that they're going to make sense? And in particular, even if you tell everybody, okay, I want to know what your state is at time so and so, then that won't help, because unless their clocks are perfectly synchronized, which in practice isn't really possible, then you can't get a coherent picture. So one reason why it's called a snapshot algorithm, and I could use an analogy which was actually used in the original paper about snapshots. Let's say that you want to take a panoramic photo of a bunch of birds flying through the sky, and this is Chandy and Lamport's analogy. So you can't take a picture of the whole sky at once, right? But you also don't want you also want it to be an accurate picture, right? Like, you don't want the same bird to appear twice in the picture, and you don't want to leave out any birds. So how do you do it? Like, how do you stitch together all of those pictures into one coherent photo? And so this algorithm provides a way to take individual snapshots on the different processes in a way that you can stitch them together. Now, you might ask, wait, like, why do you need a global snapshot of the system? So, well, one reason is that so there's kind of two reasons, right? So in debugging, you often encounter this situation where something goes wrong, and then from that point onwards, it's like after a given point, things are wrong from that point forward. So if you want to know if that bug happened at some point in the past, right, you need to know a snapshot of the system right now to know if that bug ever occurred. So an example of that might be deadlock, right? So if you have some kind of deadlock, and at some point in the past a deadlock happened and now things are deadlocked, you might want to take a snapshot and then of the system in its current state. And a deadlock would be, I guess, like one process is waiting for two processes are each waiting on the other for something. So one way to try to figure out if you have such a deadlock going on right now in your system is to take a snapshot and then inspect the snapshot for deadlocks. Yeah, so one person just asked in chat, so a marker message is considered seen by a process also when that process has sent it out as well. That's correct, yeah. So sending a marker message counts as seeing. I haven't been looking at Twitch chat at all, so there could be like all kinds of stuff being said there. I'll take a look at it now. Okay. So I want to start to walk through a fancier example. Oh, that's funny. So somebody did ask a question in Twitch chat but then as soon as I went to VOD view, the question disappeared. So I don't know what happened there. Maybe it'll reappear, or maybe ask your question again, viewer. All right. So this is an example of a run of the Chandy-Lamport algorithm that I've seen other people use. And I even wrote a whole blog post about it. And I think it's a good example, but I don't think it's necessarily always well explained. So I'm going to try to explain it in a way that I think makes sense. So this is seriously a commonly used example. Like if you look online for lecture notes about the Chandy-Lamport algorithm, there are multiple people who use this exact example. And I think it was originally from Indy Gupta, so thanks to him for coming up with it. Okay. So here's our set of events. We got 3 processes. We've got a bunch of events, A through K. We'll say that process 1 is the initiator. Oh, okay. The question on Twitch chat is back. So the question was, once you've marked a channel empty, what happens if you received another message on that channel? Do you just ignore it? Yes, that is exactly what you do. So once a channel has been marked as empty, you're done with that channel. So that could happen, right? And it would mean that your snapshot wouldn't necessarily be the most up-to-date snapshot, but it would still be a consistent snapshot in the sense that it would be coherent with the other snapshots that you're stitching it together with. Another question on Slack is, what happens when 2 processes initiate at once? So that actually turns out to not be a problem. And if we get a chance, we'll look at a more detailed example of that. But if you want to, you can look at the rules that we wrote down and try to work it out yourself and say, okay, suppose these 2 processes both decide to be the initiator. It turns out that that's actually okay. They can both send marker messages, and it's okay if there's not even any distinguishing between the marker messages from them both. Like it ends up actually working out and producing a coherent snapshot. That's one of the most fascinating things about this algorithm from my point of view. So we're going to be talking about many distributed algorithms in this course, but some distributed algorithms are also what I would call decentralized algorithms. And by decentralized, I mean that anyone can start them, right? There's no like designated coordinator who has to be in charge. And so decentralized algorithms are like a subset of distributed algorithms, and they're often they have to be written in this really interesting way that makes it possible for anyone or multiple participants at once to initiate them. And that's actually true of this algorithm, which is one of the things that I think makes it so cool. Okay, so let's do this. Let's say that P1 is the initiator, and let's say that it initiates a snapshot right here, right after event B. Okay, we'll call that S1, the snapshot that it takes of its own state right there. Okay, so what does P1 do? It records its own state. It's going to send markers out to process 2 and process 3, and it's going to start recording on its incoming channels. So right here, it's going to send marker messages out. So let's say that it sends a marker like this over to process 3. In my example, the marker messages, ignore the fact that that's a curvy line. In my example, it I want to be faithful to the example that I wrote up before, and in my example, the marker message arrives before event J on process 3. And then this other marker message, we're going to imagine that this one is a little bit slow. So it actually takes all the way to after event H on process 2 to arrive. So it sends its markers out, and it starts recording on its incoming channels. So process 1 has 2 incoming channels, right? C21 and C31. So right now, both of those are recording, and so they're both empty for now. By the way, how many marker messages do you think this algorithm is eventually going to send? Yeah, so this one will send 6, right? In general, everybody has to send a marker to everybody else, right? So if there are n processes, all of them are going to send n-1 marker messages. Yeah. So in general, it's going to be n times n-1. So that's a lot, right? So in this case, that'll be 6, right? Because 3 times 2 is 6. But yeah, in general, it's going to send this quadratic number of marker messages. And this is, I think, typical of distributed algorithms, and especially of decentralized algorithms. They have to send a lot of messages in order to work. So this algorithm is not necessarily what you might call efficient, but you can't actually do any better. Okay, so back to the algorithm. So I intentionally made this one here slow so you can see that the algorithm will still work even if it takes a while for the messages to arrive. By the way, this algorithm does actually assume that messages don't get lost. So we talked about reliable delivery really briefly before. This algorithm assumes that we have reliable delivery of messages, but they could be slow. Okay, let's talk about what happens right here on P3. P3 gets the marker message. Oh, n here, somebody was asking in chat. N is just the number of processes in this system. So the number of messages, the number of marker messages that get sent by this algorithm is n times n-1 if n is the number of processes that are participating. Okay, so here. So P3 gets the marker message right here. What happens? Has P3 ever seen a marker message before? No. So what does it do? It records its own state. We'll call that S3. And now it has to send marker messages on its outgoing channels to P2 and P1. And it has to start recording incoming messages on all of its incoming channels except the one that it received the marker message on. So it received the marker message on this channel, but it has another incoming channel, right, from process 2. So it has to start recording on channel C23. So C13 is going to be empty because that's the one that it received the marker message on. C23, it's recording. And now it's going to send its marker messages out, right? So its marker messages are going to go out to P1 and P2. Let's say that they go like this. So there are those marker messages. But by the time we're done, we're going to have 6 squiggly lines on this picture. So let's look at P1. Here's where the marker message arrived on P1. This marker message is not the first that P1 has seen because P1 originally sent them. So what does P1 do? Can somebody refresh my memory? What does a process do when it receives a marker message and it's not the first marker message that it's originally seen? Yeah, so it has to stop recording on that channel. So it was recording, right, on this channel C31, which was the channel from P3. So it's going to stop recording on that channel. It didn't receive any messages on that channel while it was recording anyway. So C31 state is now empty. Okay. Now let's look at the marker message from P3 to P2, this one that came in right here. What does P2 do when it gets that marker message? Yeah, it has to record its state. It didn't do that yet, so it had better do that. So finally, P2 gets to record its state. And it's going to loop up all these events here. And then what it does is it marks the state of the channel that the marker arrived on as empty. The channel that the marker arrived on was the channel from P3. So C32 is empty. And then its other incoming channel was C12, right? The channel from process 1. So it's now recording on that channel, and it has to send out its own marker messages on its own outgoing channels to P1 and P3. Let's say that those get sent right here. Okay, so this is the current state of the system. And now this marker message that we sent from P1 way back a long time ago finally gets to P2 right here. So because P2 has already seen a marker, what does it do in this case? Yeah, so it can stop recording, right, on the channel that the marker came in on, which was C12, right? That was this one here. But it has to set the final state there as all of the incoming messages that arrived on that channel since recording began. So were any messages received on this channel C12 since recording began? Doesn't look like it to me. It started recording right here when it started taking this, when it got its first marker message, so it didn't receive any. So I think that this can now be marked as empty as well. Okay, now what? So now process 2's job is done, right? It recorded its own state, and both of its incoming channels are now done. They're both marked as empty. But we still have 2 things to finish up, right? We still have process 1 has a channel that's still recording, and process 3 has a channel that's still recording. Well, that's handled by the fact that these marker messages right here were sent out from P2. So P1 needs to finish up. It was waiting for this marker to come in from process 2 so that it could stop recording on channel 2.1. And look, there's that marker message. So did anything get recorded on channel 2.1 while it was recording? It started recording way up here. Did anything get recorded on that channel? Yeah. So there was this message right here, right? Whose send was H and receive was D, right? So that should go into C21's final channel state. So this message H to D here. Okay. And then finally P3 gets the last marker message that it was waiting for from P2. Did any messages come in on P3 while it was recording on that channel? Doesn't look like it to me. So no messages came in there while it was recording. So this can be empty as well. Okay, so now all of the process states, S1, S2, and S3 are recorded, and all of the channel states are recorded. So we're done. So I want to address a question that came up in chat. So somebody asked, there's actually a couple of good questions here. One person asked, can you have multiple executions of the algorithm running concurrently? So yeah, absolutely you can. So that's kind of what I was getting at when I said that this algorithm could be decentralized, right? So it turns out that it's actually okay if process 1 decided to initiate this snapshot right here, and process 3 over here of its own volition decided that it was also going to initiate a snapshot, and they both decided to snapshot their own state and send out marker messages, it turns out that that actually still works. So that's one of the really appealing aspects of this algorithm. Let me see if there were any questions that I missed on Slack. Somebody asked, the channel is the channel marked empty before and after the trading of the marker messages? So our rule for when things are set to empty, to go back to the what I wrote out before, so that happens when you get a marker message and it's the first marker message you've ever seen. At that point, you mark the channel that the marker message came in on as empty. So when you get a marker message on a channel, that's when you can that's when you can mark it as empty. So the question was like, the channel is marked empty before and after the trading of marker messages? I'm not sure. Oh, so here's another great question in chat. How does the entire system know when the snapshot is done? Great question. So, well, when does a given process know that it's done? Yeah, so, well, you know that you're done. Okay, so somebody said when it's received n-1 markers. So you definitely have to have received n-1 markers. So, and then somebody else said all incoming channels marked empty. Well, no, not necessarily, right? Because like the state might end up being something like this, right? Where it's not empty. So I would say a process knows it's done when it's recorded its own state and it's recorded the state of all of its incoming channels. So you might not know what's going on anywhere else, right? But you know that you're done when you've recorded your own state and you've recorded the state of all your incoming channels. So just like we don't have a global clock in a distributed system, we also, unless you decided to have some coordinator process that went out and checked with everybody and said, okay, are you done snapshotting yourself? And you could have that, right? That could be something you could do. But then that would introduce because you had this single coordinator process. What if the coordinator failed, right? So that's something that you could do. So what you would do is you would run the snapshot algorithm to have everybody snapshot their own state. And then if you wanted to, then you could maybe like elect somebody to be the coordinator, and then have that coordinator go out and collect up all of the snapshots that were taken on the individual states. So there's kind of two questions here. Like, how does the entire system know when the snapshot is done? So that's kind of a problem that gets solved externally to the Chandy-Lamport algorithm. So all the Chandy-Lamport algorithm does is establish a way for every process to take its own individual snapshot, such that when those snapshots are later stitched together by something external to the algorithm, then they'll make sense. So that's kind of a separate problem. But the other issue is, do you know that this actually terminates? So it turns out that it does, and there's a proof of that in the paper by Chandy and Lamport. But we'll kind of give an informal argument as to why it does. So before I move on, I want to ask a quiz question. So here is today's quiz question. Which I will share in chat. We'll wait another couple minutes. Oh, so there's a question in chat, which is, why doesn't the algorithm record internal events like C or J? So going back to the picture. So we had a couple of internal events in this picture where C or J. Wouldn't we expect snapshots to do that? Yeah, absolutely we would. The only reason that they didn't get recorded is because that's not the moment that the markers arrived. So at the moment when P1 decided to snapshot its own state, C hadn't happened yet, right? And then at the moment when this marker arrived over here on P3, J hadn't happened yet. But if it had, then yeah, absolutely that would have been included. So if there had been some internal event right here, call it L, on process 2, then that definitely would have been included in the snapshot. It's just that in this particular picture, it happened not to have been. All right, so I want to talk a little bit about these big picture things that we talked about briefly. We're almost out of time, but I want to talk about this question of the Chandy-Lamport algorithm terminating. So this algorithm, what do you think? Do you think this algorithm is guaranteed to terminate? Well, okay, so what does it have to do, right? Well, it has to record the state of every process, and it has to record the state of every channel. So you can kind of think about termination on this per process basis, right? So a particular process is responsible for recording its own state, and it's responsible for recording the state of its incoming channels. So the informal argument for termination is, if that terminates for every process, if recording its own state and the state of its incoming channels terminates, then if you can ensure that every process can take care of the piece of the overall picture that it's responsible for, then we know that the whole thing can terminate. So what's the argument for every process being able to take care of its own piece? Well, it's pretty straightforward, right? Like recording its own state is easy. We're assuming that messages are reliably delivered, right? And we're assuming so we're making a lot of assumptions here. We're assuming that the messages are reliably delivered. We're also assuming that processes don't crash. So we'll come back to that later. But sooner or later, every process should receive a marker message on all of its incoming channels. And then the other piece that you have to get done is recording the state of the channels. You know it's okay to stop recording on a channel when you receive a marker. Basically, everybody, we know that everybody receives a marker on every one of its incoming channels because the algorithm has every process send a marker out on all its outgoing channels. And one process's outgoing channel is somebody else's incoming channel. So that's an informal argument for the Chandy-Lamport algorithm terminating. We're going to talk more about this next time, and we're going to talk more about the assumptions that this algorithm makes. But we're out of time for today. So next time, we're going to talk more about these kind of big picture aspects of this algorithm, and we'll talk a little bit more about something else that came up today, which was what I just said about this assumption that processes don't crash. And that will hopefully lead us a little bit more into the next part of the course, which is going to talk more about failure. So I'll see you next time.